Maven project scientist at Goddard Space Flight Center. He has been detailed to NASA headquarters working in the ionosphere, magnetosphere, heliophysics, and planetary atmosphere divisions. He was co-investigator on the Pioneer Venus Orbiter mission. Please welcome Dr. Grebowsky.
I welcome you all to the launch of the next extensive investigation of Mars, Maven. And if you want to wow your friends, you could call it by its name. In fact, I don't remember its name sometimes. But as you saw in the previous talk, there is strong evidence of water. There's also strong evidence of public interest in Mars, you see in this slide. We have seniors using it. Originally, there was, in Viking 1, they saw pictures of the surface, and they saw faces in that, and the whole community was all excited there's life on Mars, and it turned out Mars Geographic Surveyor actually showed they're just arbitrary shadows, but everybody got excited about the faces on Mars. Back in the old days, you all know about the canals on Mars. They had weak telescope observations, and they said there were canals. It has to be humans that are doing it. War of the Worlds, and there are a lot of science fiction books, and I really didn't know if this is from Doctor Who, but I just thought it was an outhouse or a telephone booth on the surface. I never watched Doctor Who, and I was just told what it was about. But comparing the Earth with Mars, it is a size comparison. Keep this in mind, it's very important. The Earth has a lot of clouds, a lot of water. Mars is dry at the present time. There's ice on the polar caps, the white stuff on the polar caps. But look at the size. There's a half a difference between them. That means the gravity on Mars is less than on Earth. A 160-pound individual on Earth would weigh about 60 pounds on Mars, okay? So it's not holding things down as well as the Earth does. Now we have evidence, what you saw in the previous presentation, I think it's confirmed that there was water in the past on Mars. There's no doubt about it. This is an example on the upper left of rills, and they have, well, as was shown before, if you fly in an airplane, you see water, rivers turning like this. There's evidence of this. There's evidence of lakes. And the question is, where did the water go? But it's also a case, to have liquid water on a planet, you have to have an atmosphere dense like Earth and maybe hot like Earth. So it had to have a dense atmosphere. Right now, it's about 1,000 times weaker than Earth's atmosphere in terms of pressure. And that's why you can't have liquid water. It either becomes ice or it just vaporizes, like in wintertime when your snow evaporates without melting, sublimates. So you can't have water at the present time, but there's evidence we had in the past. On the bottom, they found carbonate deposits. This means there's carbon dioxide that actually went to the surface. But the amount of carbon dioxide in the surface that they find is not sufficient to account for the disappearance of the atmosphere. And Mars, if it had an atmosphere, it's probably CO2. It would be like Earth at the very beginning, too. It's a greenhouse type effect. It would be CO2. The Earth was CO2 at the beginning also, when it had high pressures. So we had a lot of carbon dioxide in the past, but there's not sufficient carbon compounds in the surface to account for the disappearance of carbon dioxide. And recently, Mars Express, a European mission, on the upper left, forget that, on the upper left, what happens, the sun is on the right-hand side of that figure, and all the colored plots is evidence of escaping oxygen ions from the planet. Mars Express, it's statistical. The red stuff means there's a lot of it, and the blue stuff means there's a little less. But right now, there's evidence that the atmosphere is disappearing because oxygen is coming from the atmosphere. Now, what Maven's going to do, this is complex, and I just want all the vertical arrows going up. There are a lot of processes, and that's all escaping atmosphere processes. And keep in mind, the driver of the whole Earth system is the sun. The sun is throwing out UV radiation. It's like the stuff that gives you a sunburn. This heats the atmosphere, and it makes it energetic enough so the particles come out. And also the sun is like a bubbling ball. It's something like nuclear reactions blowing all the time, so it's spewing out a lot of plasma, a lot of ions, charged particles. That's the solar wind. These impact the Earth. And it's all the energy sources in. If you didn't have the sun, the Earth would be a ball of dirt or ice on the top, nothing else. Now what happens, this is modeling, what happens if the solar wind, if there's no magnetic field, this is what happens with solar wind. You can see this is the atmosphere being taken off of the planet. This is a modeling, it's fairly realistic, it fits with some of the observations we have. It's very complex, but the solar wind strips off gas from the top of the atmosphere. And the question is, why in the past they did not do this? It's because Mars has no magnetic field. The Earth has a big magnetic field surrounding the planet. And that magnetic field will hold off the solar wind charged particles. The charged particles cannot get in. So the last slide showed you what happens if you don't have a magnetic field, they strip it away. This does not happen on the Earth. So we feel water existed in liquid form on Mars when it had a magnetic field. It withstood the solar wind. But the magnetic field disappeared billions of years ago, and when it did, that seems to be the time when the liquid water disappeared, and the sun is coming in to actually blow the whole atmosphere away. Now what Maven does, these are the instruments on Maven. On the upper left, upper left-hand side, with the yellow bars, these are all the instruments that measure the solar wind. We have observations on it that measure all the properties of solar wind. On the right, we have two measurements that actually measure the atmosphere properly, so we know what the atmosphere is doing at the present time. And on the lower left, we have these ion escape processes. So the key to Maven is the sun varies all the time. So we're looking at all the escape processes in the physics for different stages of the sun. And once we find out how the escape depends upon variations in the sun, we go back in the past. We know how stars evolved going back in the past. So we can use this understanding to extrapolate back and find out when the atmosphere started to escape. So that's the purpose of Maven. And I'm trying to think, Mars atmosphere, evolution, and something like that is the name of it. While your friends look at the brochure and use that instead of Maven. It's difficult to have a conversation by using that all the time instead of Maven. And Sandra next will talk about some of the details of the spacecraft itself, the operations. Thank you.